what we're going to do now is start transitioning towards what we're going to do the rest of the day, which is focused on breakout work. We've set up the workshop to have 2 different breakout themes. The first one is on mission pull. And the intent of this session here is really to focus on missions that we are thinking about or would like to do. Kind of as Jeff and as Ariel pointed out, there are some missions out there that fundamentally will require the use of autonomy on board to be able to accomplish some of the things that we want these missions to do. And so what we're going to do now is we're going to, for the next half hour, have 5 overviews of 5 different mission categories, or you might want to think of these as different science disciplines. And then after that, we're going to break up into small groups. When you all came today, you should have received a new badge. If you haven't, after these overview talks, please go out to the front and you'll get assigned a number. Those are going to be the groups that you spend time working together, and I'll tell you more about that after we get through the first set of talks. So to start with, we're going to have Mike Little come up and tell us about Earth science. He's got a number of things he wants to try to cover in 5-ish minutes, which will seem a long time after just the 2-minute talks. But Mike.
Thanks.
And this is forward and spec.
Okay, thanks. So I like to scare the sponsor of these programs. I every day enjoy scaring Mike Seablum, but I got a chance to scare Terry because I sent him like 25 slides and said, I'll do that in 5 minutes. But the first slide is really the important one for the mission that I want to talk about, which is an effort to integrate from different vantage points lots of different Earth sensing data, some of it from satellites, some of it from in situ measurements, and some of it from aircraft, which we'd like to be able to task automatically or using autonomy and send them off to go make measurements that we might need. So picture the way we do weather forecasts today. Is anybody a meteorologist besides Singdar in the room? Okay, so, oh yeah, that's right, Seablum is, so I'm gonna scare him again. The way we do it today is we collect a bunch of data from observations, we shove it into an assimilation model, and then we take the output of that model and we shove it into the weather forecasting tool. And we do that about depending on what you're doing, about every 4 to 8 hours, and then we spit out a bunch of forecasts from that. What we'd like to be able to do is start looking at this as more of a continuous process and continuously update the data that's going into the system. And there's a technique called skill level that allows you to measure how good your weather forecast actually is. And so if you were doing this continuously for different regions, you could say, gee, my weather forecast for Hawaii is starting to really fall apart. I really need to get some new information in order to stick it into that forecast and really improve it. And so I could say, gee, you know, I really need to get sea surface temperature and surface winds over the Sea of Japan. What's the best asset I can get to use in order to make those measurements in the next 20 minutes so that I can improve my weather forecast? And so what we'd like to be able to do is have the system in an autonomous way either decide it's going to be off of a satellite that's coming up, or I'm going to launch an aircraft from Yokosuka Air Force or Navy base and have it go make those measurements, or I've got some buoys that are going to give me some decent information. And so now I can update the weather forecast fairly quickly and keep that skill level up continuously instead of, you know, the current version of every 4 hours. Some of the other slides that are in here are for you all to take a look at in your spare time and understand a little bit better some of the things that we're doing in Earth science. So, Terry, you're gone. Where are you? You expected me to talk much longer, didn't you?
Great, thank you very much.
You bet.
Hey, Mike, I've got a question.
Yes, sir.
Any interest or express interest to do anything out of ESTO to make sensor webs and autonomy more real or more practical?
So in the 8-second version of that answer, yes, we do, and we have been for the past, 12 or 15 years, sort of, with sensor webs in particular. But yes, a lot of interest in that area.
All right, next we're going to have Carolyn Mercer tell us a bit about Europa. We actually gave you extra time.
Thanks, that's good.
This is forward and back.
Okay.
Can we have Carolyn's charts up?
Oh, I get to go through 25 charts. Is that right?
Actually, they'll switch them back here. Can we please switch to the Europa presentation?
But we can show Mike's movie in the
We'll show
meantime.
Mike's movie while I run back. You have no control.
I have no control. So let me say that I'm Carolyn Mercer. I am managing technology for the Planetary Science Division out at NASA headquarters. I'm standing in for Joan Salute, who is the program executive for the Europa lander mission. This mission is a mission that is in pre-formulation right now, and she regrets being here because she believes that autonomy is critically important for this mission, and I'm really happy to give you an overview of what's going on. The Europa lander mission, here we go. It's, again, a mission in pre-formulation. It's being led out of JPL, and the team, the full team, you can see on the upper, that corner there. Sam Thurmond is the project manager at JPL for this pre-formulation mission, and also in the audience is Glenn Reeves, who is managing the autonomy. So it is a big mission, both the size of the spacecraft, but mostly in the grandeur of the mission objective, which is to define, is to search for evidence of life on this ocean world that is orbiting Jupiter. So searching for the evidence of life, also assessing the habitability of Europa, and then also characterizing the surface and the environment for future missions to Europa. So a science definition team has been stood up to take those goals and break them down into objectives. You can see them there on the outer ring of this nice diagram. I should say that these charts that I'm showing you here were presented at the Mission Concept Review last month. So to search for evidence of life, we're looking for organic, inorganic, and morphological indicators, and also determining the provenance of those measurements to determine, do they make sense? What's the context in which we found them? We're looking for habitability to assess the non-ice composition of the regolith and determining the proximity to liquid water, and also assessing the physical properties and the dynamic processes of the surface and subsurface for future missions. You can see here that the STT came up with a suite of instruments that if we could fly all of these things, then we could satisfy all of these objectives. This is a package that fits nominally into, fits into the nominally 45 kilogram science payload allocated for the mission. So as envisioned now, the Europa lander mission would fly after the Europa Clipper mission. The Clipper mission has a launch readiness date of 2022, and it's going to be an orbiting mission that's going to be assessing the habitability of Europa. The lander mission is battery powered, and right now it has an expected lifetime of 20 to 30 days, and that's based on how the scientists intend to use the science instruments and the acquisition system. The baseline science includes the acquisition and analysis of 5 samples, each of about 7 cubic centimeters each, and the samples are going to be acquired subsurface. So we want to go at least 10 centimeters below the surface to get below the irradiated portion of the regolith, and also to acquire samples from at least 5 regions within the nominally 2 square meter reach of the lander. So again, it's envisioned this would launch off of an SLS Block 1B in late 2025, take about 4.5 years to get to Jupiter, so that the earliest landing on Jupiter would be December 2031. As envisioned, there are 2 spacecraft in this mission. There's the lander, and then there's a carrier vehicle. The carrier would also serve as a relay orbiter to get the data to and from ground. For the lander, it uses a sky crane concept, and we would use the terrain relative navigation using high-resolution reconnaissance imagery from Europa Clipper, and then also on the way down, we'd be using a LiDAR system for hazard detection and avoidance. The carrier relay orbit is a couple of thousand kilometers above the surface, and it would provide about 10 hours of continuous operation or coverage per orbit, and each orbit is about a day. Over 3 to 4 gigabytes are expected for the data return. So the surface overview, which is where we think autonomy may become really critical. Once you land, we allow a day to assess the environment, check out the landscape, figure out what's going on, and then 3 days to do the first sample acquisition and analysis. That includes excavation, sample acquisition, transfer to the instrument suite, and analyzing the data as it comes in. It's during this first cycle that we're going to figure out what we didn't know before we went, because there's a lot of unknowns in this mission. After that, then we expect to get a regular cadence of taking the next 4 samples, so acquiring that data, getting it to the instruments, and analyzing it. Shown here are ground cycles, so that's a design choice. We're really interested in understanding how autonomy can improve this mission, because with only 20 to 30 days, with only 10 hours per day of ground link, with a 45-minute relay delay time, if we could include automation into this, would it be possible to increase the amount of science that we can get out of this very time-limited mission? This is a really tough challenge, because the ultimate goal here is to search for signs of life. What is a biomarker, right? That's the hard question. Automating that makes it, I don't know, is it harder? Is it easier? After the mission is complete, there's a self-incineration process to destroy any contaminants that we may have brought up from Earth. And then the relay system completes its data relay to Earth, and it disposes itself after about 30 days. Its life is limited by the high levels of radiation that it's going to experience. The key technology maturation elements include the terrain relative navigation, the landing LiDAR, the batteries. We want to maximize the length of the mission by extending the energy storage and the usage of those batteries. Of course, the low temperature sample acquisition and collection, it's very cold there, low mass and low power motor controllers, and the sterilization incinerator. Autonomy and automation could be included in the power management system of the batteries, and of course in the sample acquisition and collection and analysis. So the challenges, the role of autonomy in the sample acquisition and processing system. The current concept has ground in the loop to decide if the sample contains evidence of life from these multiple instruments, which in turn drives the decision of where to collect the next sample. If the mission is indeed limited to 20 days, then could full autonomy increase the likelihood of mission success and provide more science return for this mission? This is not an idle question to us. This is the perfect time to be having this conversation, because we're still in pre-formulation stage. We are also trying to figure out what technologies to invest in, so I look forward to a good discussion.
Thank you, Carolyn. We actually don't have time for questions here, but Carolyn is here. If you have questions about Europa, you can find her. Next up is Larry Kepko talking about heliophysics. Do you need a clicker?
Yes. All right, thanks. My name is Larry Kepko from Goddard Space Flight Center. I'm a heliophysics scientist trying to develop next generation of heliophysics missions. This has been very interesting, listening to these discussions, because I talk to our Goddard technologists quite a bit about autonomy and automation. And they come to me and says, Larry, why don't you include autonomy in your missions? I say, well, what value are you adding to my mission? And I think that's the problem that we face. It's not that I'm scared of including autonomy, it's that I don't quite see the value for heliophysics. Often when I see the value in autonomy, it's when you're interacting with the environment, right? If you're landing on Europa, you need some autonomy. If you're driving around Mars, you need autonomy. Going through the oceans of Titan, you need autonomy. If I'm flying in orbit around a planet and just collecting data, it's hard to see autonomy. I see automation. Automation's everywhere. And that's some low-hanging fruit that we don't take advantage of. I get the impression, listening to everybody here, that automation is less sexy than autonomy. But automation has an immediate impact on our missions right now that we could incorporate, and I think we should. So I'm just going to show 2 slides. This first one, this shows an MHD simulation showing Earth's magnetosphere. Just a top-down view, and the solar wind flows from left to right. The Earth is that little tiny dot, and I don't have a laser pointer, that little circle right in the middle there. See there, just to give you a sense of the scale. Right. Okay, there we go. Right, so there's the Earth. So you can see the sense of the scale of this space weather that we live in. Typically, we, just for budgetary reasons, fly one spacecraft out there and try to understand all this. It's like trying to understand the weather in Washington, D.C. by having one data point in San Francisco. It's just nearly impossible to really understand and predict. What we really want is a constellation. And you can see, just based on the grid size, we need hundreds of spacecraft. Just the scale size of the phenomenon, the things that are going on, the time scales, the spatial scales, we need hundreds of spacecraft. That's going to require lots of automation, right? Contact scheduling and prioritization. I know that's a strong point at Ames. They've been working on that. We can apply it to this mission right here very clearly. Orbit maintenance is not something that might be obvious, but at these distances, we start to get lunar perturbations. No spacecraft tend to pop out of the ecliptic. Again, orbit maintenance of hundreds of spacecraft is a little involved for people. It's not autonomy necessarily, it's automation. And beyond that, I struggle. I struggle to see where autonomy comes into missions like this. This is MagCon. It's been looked at for 2 decades. Just for budget reasons, we're looking at 36 spacecraft. That's already a multi-billion-dollar mission. In the future, I think we like to have 100, usually in small sats. We also have constellations in low Earth orbit. And there, again, it's automation. If I see an event somewhere, I can't move my spacecraft. I'm constrained by orbital dynamics. I don't get to drive somewhere else. But automation really works there. The area where we might see a little bit of autonomy is with space weather. And sometime in the future, we as humans will be exploring the solar system. We'll be out there at Mars or wherever we'll be. And we may not be near the Earth. Right? Mars is often on the other side of the sun. We can't communicate. And we live in this, let's see if I can go back and forth and get play again. There we go. And what you're seeing here is the solar wind velocity. And those are coronal mass ejections. And this is a model. Coronal mass ejections coming off, and here's the Earth. This was a very large event that happened a couple years ago. And if it hit the Earth, people think it may have been equivalent to the Carrington event and caused a lot of damage to us. Right? Let's see if it plays again. It's nice to look at. So as we start exploring the solar system, we'll need to have space weather buoys, space weather monitors, right, to really measure this stuff. We can't measure this. This is one spacecraft that actually saw it, because we have a spacecraft there. You can imagine this region being filled with spacecraft, operating autonomously in this case, because you do want them to monitor space weather. You want them to look at the sun and say, here comes an active region. It's starting to emerge. And based on some model, some basic physics, it'll say, I think a solar flare is about to go off in a day. I think it's going to be a CME in a day. And I'm going to automatically tell the astronauts that are on the other side of the sun from the Earth that, hey, something's coming. Because I can't see what's on the other side of the sun. I need that spacecraft out there to really look at it. So there's some autonomy there that we could really think about, interacting closely with models in the same way that you do with the sensor web on that Earth science talk we heard earlier. Event identification, data reduction to close the comm links, that's again, another no-brainer. Right? We collect a lot of data, a lot of multispectral data, imaging data. We can't send it all down. Autonomous data identification, event identification, that stuff, again, to me, low-hanging fruit. We can do that now, I think, and pull that down. So I think my challenge to the autonomy community is, what can you give me now, today, that we can really infuse right now? I think there are things there, but I think often we get sucked off into really cool technologies. But there are things that we can do today. Right? Thanks.
Becky? Can we get the next presentation up, please? This is right? Perfect. Yeah, great. It's all yours.
All right, thanks.
Yeah,
This is
pull
the
it
one.
back, and if you need a white laser pointer, this button.
Okay, thank you. All right, I'm Becky Castano. Unfortunately, Pat Beecham was unable to be here today. So I'm just going to talk a little bit about some of the concepts for outer planets and from the Outer Planets Assessment Group and how autonomy might be valuable there. Just wanted to start off by reiterating with the decadal survey, the past decadal survey, which advocated for consistent and steady funding into the development of new technologies, which in fact has been certainly happening. And then emphasize that there were 4 main criteria for the missions that were going to be proposed or suggested, including science return per dollar, programmatic balance, technology readiness, and then availability of trajectories to get there. So again, autonomy, assuming that we can get it, achieve the technological readiness, has the potential to improve upon the science return per dollar. And again, advances in a number of areas were called out, including spacecraft autonomy. So when we're looking at the outer planets, one of the things that Terry had mentioned is one of the needs for autonomy is sometimes when your cadence of needing to command a spacecraft is higher than your communication opportunities. So as you go out to the outer planets regions, of course, your light time significantly increases. From the Jupiter, 20 to 45 minutes out all the way to Pluto and then beyond in a matter of hours. And so looking at places where we would need autonomy is when there's changes in the spacecraft or the environment that are happening and that are not predictable, so we can't define those ahead, and then we need to respond before the next kind of comm cycle. So we have a number of cases of that in the case of outer planets. The outer planets, just to give an overview, is of course not like one venue like the Mars or Venus, but there's a lot of bodies, there's a lot of planets, well, a number of planets, and then a lot of satellites to observe. And so when you're looking at competed missions, there's a lot of diversity of things that are proposed, and only a limited number of selections, obviously, based on money that can happen. So as we know, Europa Clipper is currently in phase B, and as we just heard about the Europa lander. So we know about those two. But there's a lot of other different bodies and also other more advanced kind of exciting things that one could do with even Europa. So kind of in the outer planets world, there's a lot of focus on the ocean worlds, Europa, as we obviously heard about, Enceladus, Titan. And then there's some discussion on the ice giants, Uranus and Neptune, and then there's a lot of talk about also the dwarf planets. So I want to just go into a little bit of how the potential benefits of autonomy for the outer planets, kind of in working with ESA and others. We have come up with 4 different areas, things that you can do, you couldn't do before, so new science. Examples are given here: autonomous landing on Europa, small body proxops, navigating extreme terrains, and then a planetary sample return. Then there's types of capabilities that you can do more science, increase the capabilities, instrument pointing autonomously, fast traverses, maybe multiple target selections. Then there's just ensuring more increased robustness. So how do you, one of the examples here is automatic trajectory corrections. Flying through failures especially comes into play when you're at uncertain environments like Europa. How do you handle spacecraft degradation? And then there's just the cost-effective science. How can we do things more cost-effectively? Examples are lights-out communications. This especially comes into play as it takes so long to get out to these outer planet targets, so that how operations becomes, in cases, quite expensive just during the cruise phase. So how can we reduce those costs? And then I think it's been a little bit implied here, but how can we command at high-level goals? Right now we do these careful individual sequences. How can we maybe give a spacecraft high-level goals and be ensured that those are going to be executed? So now I'm just going to go into 3 example areas. First of all, we've talked about the ocean worlds. There's interest here in the remote sensing, aerial and landed missions, depending on the various bodies. A lot of times these ones with the ocean worlds, we're searching for signs of life. So there's above surface and aerial, and then of course, I mean, we would like to get down to these ocean worlds. We would like to eventually one day get down to those oceans, which is no small feat. So all these would take system level reasoning and decision making, science planning, summarization, data prioritization, and then perception-based mobility, manipulation, and handling. You notice in the Europa, it's not an EDL, not an entry descent, but more of a deorbit descent and landing. So that, and then with Titan, there's as an example of a heavy atmosphere, there's aerial vehicles, which again, you're not going to be able to command that if you're having any aerial vehicle that it's in the dynamic atmosphere. You're not going to be able to command that from Earth. It's going to have to be able to operate. And then even things like Triton, where we have even less information. So one example that there's been a lot of study on, that's a very high interest area, is the Saturn system and especially Titan. So one of the concepts that has been studied considerably would involve multi-asset missions. So there would be an orbiter above the atmosphere that could dip down. Then we would have an aerial vehicle, examples like the balloon shown here, and then a lander, which could be like going on the lakes or on dry lake bed or the shore. And all of these especially are going to be both coordinated and requiring individual capabilities of autonomy, automatically determining the targets, for example, and then or following up with science measurements, selecting what data to come back, location and altitude control. And finally, there's the ice giants, which there's been more recent studies. It's been pointed out that ice giants Uranus and Neptune, while we have studied with Voyagers, there's never been a specific mission to either of these planets or their systems. And so Science Definition Team recently identified 12 high priority science objectives, 2 of which are the highest priority ones are listed here. Constraining the structure and characteristics of the planet's interior, including layering, and then determining the bulk planet's compositions. One among the interests in these areas is that, again, it was mentioned earlier with the exoplanets that have been discovered. There's been over 3,000 exoplanets that have been identified, and the majority of them fall into this category of what fit the characteristics of these ice giants. And so this offers a big opportunity to study them, to learn more about those exoplanets. And finally, just as a summary, autonomy will be critical for exploring these outer planets. We'll have, as mentioned, considerably less information about the environment that we're going to, especially when we're going to these landed and in situ situations. Like when we went to Mars, we had tons of flights beforehand. And so Ocean Worlds is going to take not just getting there, the autonomy, but also mobility. So, and autonomy is needed system all the way down through the subsystem levels. So, thank you.
All right, and the last mission overview is Gary Hunter. He'll be telling us about Venus. We could have Gary's charts up.
Please? Okay.
Forward, back. Do you need a laser pointer?
Laser pointers.
Right here.
I thank you very much. Hi, I'm Gary Hunter. I'm representing the Venus Exploration Analysis Group, VEXAG. I'd like to thank Jim Cutts from JPL and Sanjay LeMay for input to this particular presentation. And what I'm attempting to represent, let's see if this works, is Venus mission concepts that might have use of autonomy. And as a background, Venus exploration is challenged by a range of environments within the Venus system. As you go from the top, effectively from the upper atmosphere down to the surface, you have significant changes in what it is you're attempting to deal with in exploring Venus. We've looked at it as, in a sense, and just to break it apart, as 3 separate regimes that one might look at. One is an orbiter regime, where the orbiters operate above the Venus atmosphere and may have different types of orbit, whether it be elliptical, circular, etc. Orbiters may also dip briefly into the atmosphere to sample the atmosphere. Mid-atmosphere, 50 to 75, has benign temperatures and is accessible to aerial platforms such as balloons, airplanes, and gliders, and in fact, it's very much like Earth. Descent with some notable differences like high speeds and sulfuric acids, but nonetheless, it is very, you can begin to think of airplanes, yeah, not much, right? But you can begin to think of having airplanes, and you can think of, and they've had balloons and other forms of systems in the mid-atmosphere. And descent on surface, you're talking about then 465 degrees C, 92 atmospheres, a very harsh environment. So as you go from effectively from the orbiter to the surface, you're dealing with a range of different challenges in doing science in those environments. Planetary PSDS-3, Carolyn Mercer, has kindly funded multiple Venus studies investing different aspects of Venus planetary scientists. This presentation is going to use these three categories, orbital, mid-atmosphere, descent, and surface, to talk about uses of autonomy for Venus explorations. The applications described are meant to be notional examples of how autonomy may be used given the unique and very, very different, as you go from the orbiters to the surface, environmental conditions of Venus. The potential use of autonomy, which I view as situational awareness, decision-making, and response, in these examples varies in complexity and level of autonomy. Maybe some of it's closer to automation, some of it maybe more decision-making. But the idea is if you start to bring smarts into the system and making local decisions, what type of impact can you have? So, orbital mission concept. Noted on the side here are some of the studies that are being funded under PSDS-3, associated with generally orbiters. And what one wants to do with an orbital mission, you're operating at high elevation, while similar to the challenges for other orbiters for other planets, the thick atmosphere of Venus provides unique differences. As I said, by the time you get to the surface, you're dealing with 92 atmospheres. So the use of autonomy for Venus orbiter mission concepts could include automated location of desired target in the image, a framing camera, for image navigation and reducing data volume as needed. Optimized data communication, such as using the actual measured signal from infrared or optical sensors, boresighted with other imagers. In other words, have sometimes the focus of a particular optical instrument may not be where you want it to be. You won't know until you get the image back. Let it be autonomous. Make sure you can look at what you want to look at. Control and optimization of probe operation for brief excursions into the upper atmosphere. If you're going to do a dip and grab some atmosphere, then make sure that you've actually dipped and grabbed what you wanted to grab. Autonomous onboard detection of events such as quakes and volcanic eruptions based on processing of signals on the spacecraft to avoid the need of sending large volumes of data to Earth for processing and signaling underground. We'll come back to this as we go. Within the last few years, there's been a study suggesting that you may be able to do seismometry from not only the upper atmosphere, but the middle atmosphere and the ground. That is something different from Venus, and in particular, in this part, generated by the idea that it has this very thick atmosphere. So, mid-atmosphere, as I mentioned, the air system, it is very similar to the Earth's upper atmosphere in a number of ways, and the air systems can range from floating to controlled flight. So some autonomy concepts could be altitude and mission control of Venus balloon, including optimization of atmospheric sampling, power handling and conservation, and attitude adjustment for characterization of atmospheric flow streams. And it could be extended to coordination of multiple balloons. You could have multiple balloons, in other words, in the surface, correlate their sampling, their power, and coordination with each other. Another one, there's a picture of literally a Venus airplane. The idea that indeed it is similar enough to Earth that you can imagine a solar airplane operating for continuous periods of time. But then the problem would be is if you're flying an airplane, what if something happens? It has to be able to control its flight. It has to be able to not fall. And so, and this is similar to some of the issues in aeronautics for autonomous flight vehicles. How do they respond to unexpected conditions in a relatively short period of time and still maintain the mission? And then another example is, it's been discussed, a twister type concept from the movie, multiple little probes within the environment, multiple little probes sampling data locally and providing a picture across both height and latitude of the Venus surface. Well, you can imagine swarm coordination between multiple small atmospheric probes released within the Venus atmosphere. And then descent and surface concept. SAVE is a study that is being done under PSDS-3. Likewise, something called LISSI, a long-lived surface lander, is under development at this point. The idea is that when you get to as you go down to the surface, there is interest in understanding the atmosphere profile as you go down. And once you stay there, the electronics so far, and just recently developed, are relatively simple. So there's less autonomy in terms of long-lived missions, perhaps, with sitting at the surface. But getting on down there, there's also, by the way, other types of concepts from the flagship study. We have a much more complex system, much larger system that has insulation associated with it. And they've lasted on the order of approximately 2 hours in previous times, all the way back into the previous Russian mission. So when you have an autonomous lander that's going to operate for 2 hours, you want to make the most amount of that time in terms of getting data, validating the data, and repeating experiments as needed. You may also want to have a autonomous sampling system that handling drill locations, sample acquisition, handling, and analysis from such a system. But say you're dealing with a mixed system, a long-lived lander that may have some components on it that are shorter lived, that as it comes down, it may want to take data. It may want to take pictures when it lands. An autonomous method of assessing image quality to select the 5 best descent images for immediate return. And as you go from the conventional systems, which are going to die as it gets closer to the surface, and some of these newer systems in terms of high temperature electronics and such, can you streamline the process as you transition from stuff that lives for a short time and stuff that might live for much longer? A concept that's been discussed is a synergy between mission modes. Is the idea, and I mentioned briefly a study previously associated with seismology. This is the suggestion might be is that you could imagine a mission concept that has an orbiter, some balloon system, and a surface seismology system. And what you might want to do is correlate the data from the same phenomena at 3 vantage points: orbiter, mid-atmosphere, surface, detection of a Venus quake from an optical signal from the orbit, infrasound signal from the balloon, and seismic signal from a surface platform. The use of autonomy for these observations is an effective way of reducing demands on data return to the Earth by searching for correlated signals depending on the position of the quake, and providing in this coordinated fashion complementary measurements. The orbital station can have a broad view. The balloon station drifts around the planet. It can detect low sensitivity seismic areas. And the surface station can measure motions in all 3 dimensions needed for detailed monitoring. This is an idea where you mix all 3 of what I've talked about in the other slides: orbiter, mid-atmosphere, surface, coordinate them together, have them in effect talk to each other, at least in some fashion, and that is another possible use of autonomy. So the idea then is that autonomy may have ways to augment missions, improve the science, and we've tried to give some examples for the unique conditions of Venus. Thank you very much.
Thank you very much, Gary, and thanks everybody who gave briefings about different future mission concepts, mission areas, mission destinations. What we're going to do now is we're going to break up into small groups. You all have been assigned to small groups. We tried to keep the groups really small, like 5 to 6 people. I'm not sure, of course, if everybody who registered showed up here. So as you get into your groups, if you find out that you're really only 1 person or 2 person, then I do encourage you to go join up with other small groups. But really, we're trying to keep these groups small so you can have discussions and interaction. And there are walk-ons as well who've been assigned too. So dynamically, try to make sure that the groups only have 5 to 6 people. You all have numbers or have been assigned numbers on your tags. Groups 1 to 10 will be in here, and then 11 to 20 are in the room which is on the other side. But the overall goal here is to look, there's on the table a half piece of paper which says breakout number 1, technology pull. And this is, or really I should say mission pull here. The instructions are: 1, pick a future mission concept. It could be one of the ones that you just heard about. It could be something you heard about during the lightning talks. It could be something else completely different. But we're really trying to look at missions which currently today cannot be accomplished unless we consider the use of autonomy. And then number 2, talk a little bit about where autonomy could be applied. I think all the talks you just heard had examples of where those people believe that there are, some areas, low-hanging fruit, easy to do, well, not necessarily easy to do, at least, obvious places where we would want to consider using autonomy. Then discuss in your groups the potential benefits, the impact, the consequences, the costs, the unknowns, things you just fundamentally don't know about, and then write those all up. What we've done is we have these flip charts around here. You can make use of those. We have paper if you prefer to work that way. You're welcome to work online on a shared document, or you can write it up on your own computers. Doesn't matter. All we care about is that you, in your small groups, find a way to work productively together and generate some ideas. We've given 2 hours for this working session here, and that's because, as I mentioned at the start, you will need to leave in your small groups and go have lunch someplace. Now, if you choose to stay very close, you can go over and stay within the Ames Research Park. There is a small cafeteria near the other conference center, for those of you familiar with that. Or you could go inside to Ames, to the main cafeteria. You'll need a NASA badge to get on site. Or if you're interested in going out, there is a list of restaurants and a small map out by the front table. But we have a lot of Ames people here, and I'm sure all the Ames people will say, oh, I've got my favorite place to go. We encourage you. You can start working here. You can go off and work elsewhere. But you have 2 hours working together. And so with that, I'd like to wish you well. We will see you all back here to discuss what we've all talked about in small groups at 1:45. Okay?